So the next and last talk for this session is by Michel Boileau from Aix-Marseille Université, and he's going to talk on p-Orbifold groups and symmetric unions. So it is to you, Michel.
Okay, so thank you very much for the invitation. I am very pleased to participate to this conference in honor of Lou. In his talk, Hugh Morton said that the first time he met Lou was in this Bangor conference in 1979. And that's also my case in the sense I was a beginner. I guess Francis Bonan was also a beginner and was in this conference. And we met Lou at this occasion. And I have a proof of that. It will be perhaps the only complete proof in the talk that this photography of the people in the conference, where in some sense you can see Lou here beside José Montesinos. It's a kind of so there was plenty of people, I remember. And as you say, I remember that people were very open-minded and accessible for beginners. That was a very, very nice atmosphere. I mean. Okay, today I want to speak about a construction which is due to Kinoshita Teresaka and generalized by Christopher Lamb, which is called the symmetric union of knots, in fact, of a diagram of a knot with its mirror image. So I just start with the picture. You take a diagram of a knot. The knot is closed here by this arc. You reflect it in an axis in the plane. So you get this reflection here. And then you do the connected sum. And then when you do the connected sum here, that means that you get the connected sum of a knot with its mirror image, which is a ribbon knot. And then you insert this vertical twist, and that still continue to be a ribbon knot. So the ribbon disk for your connected sum will be twisted along this twist. So it's no longer true if you insert here a rational tangle, for example. Even if many of the things I will say work if you insert a rational tangle. But the problem we are interested in this construction, which seems when I saw it rather amazing, because when you take a knot, for example, the trivial knot, the projection may be awfully complicated. And then you choose the number of arcs you want, and you do this construction. And the problem is there some relationship between the knots that you get and the knot you start with? So I will do some. So in all my talks, the knot will not be oriented. So here, for example, if you have even number of twists, then you can put an orientation here, and if you take the right orientation here, it gives you a global orientation. But I will not do that. So the knot diagram, this is obtained from this union, is called the symmetric union of the two diagrams. The knot tip of the diagram is called the partial knot of the symmetric union. And I say the knot type because a knot type may have infinitely many diagrams. And if K admits a symmetric union diagram, then we say that it's a symmetric union presentation of K with this partial knot KD. So the trivial tangle where the twists take place are called the twist region. And the symmetric union construction depends on both the diagram D and the location of the twist region. So it's a construction which has been introduced by Kinoshita and Teresaka in 1957, and it has been generalized by Lamb in 2000. So Kinoshita and Teresaka was considering only one twist region. And there are a lot of work about when there is only one twist region in some sense. But this idea of Lamb means that in some sense you get much more knots, and also there is a priori no bound about the number of twist regions. So as I said, K will bound the ribbon disk, and you can see this. You take an arc which goes from one symmetric point to the other, and you sweep out, and you get this ribbon surface. So getting a symmetric union presentation for a knot is a way to show that this is a ribbon knot in some sense. And you have this slice ribbon conjecture. You want to show that a slice knot is a ribbon knot, but how you recognize a ribbon knot. And here you will have perhaps a way, in some sense, to see it's a knot is ribbon. And so the problem is, does every ribbon knot admit a symmetric union presentation? And it's hard to believe that. The problem, I don't see why. But if you look to symmetric unions, they are omnipresent among knots, ribbon knots, prime ribbon knots with flow crossings. So up to 10 crossings, they are all symmetric union. And for 11 and 12 crossings, they are all symmetric union except 15 ribbon knot where it's not known. Up to 11 crossing, you have only 6 ribbon knot where it's not known. And all ribbon two bridge knot are symmetric union. So in some sense, I would say it's hard to believe that the answer has to be yes, but certainly not easy to find an example. And this problem is difficult because there is no obstruction known for a ribbon knot to be a symmetric union. And also, and that's some big problem, the number of twist regions required to realize a ribbon knot as a symmetric union, there is no upper bound. So it can be arbitrarily large. So now at the moment, I guess, to show that a ribbon knot is not a symmetric union, the only way is to try to eliminate all the possibility for a knot to be the partial knot. So it means that you have to relate the knot type of the symmetric union with the knot types of the possible partial knot. And then try to get constraints to say, okay, they will not exist. But that's raised the question of the finiteness of the possible partial knots. And so, are there only finitely many partial knot types for the symmetric union presentation of a given knot? And this is not known in some sense. And so if you want to make a process to eliminate all the possibilities, that may be difficult in the sense. So first recall these results, which go back to Kinoshita Teresa K. The Alexander polynomial of a symmetric union depends only on the parities of the twist number. So for example, if the twist numbers are all even, then the polynomial is a square. This is a polynomial of the connected sum of a knot and its mirror image. So it's a square of the polynomial of the partial knot, which gives some obstruction for a knot to be the partial knot. But there is not such a result when you have some odd twist number. When you have some, this is a very bad symmetric union when you have odd twist number. And this is absolute. The determinant of a symmetric union is the square of the determinant of the partial knot. And in some sense, this is the only kind of numerical relationship between the partial knot and the symmetric union. It's the only known which is given by the determinant. This is proved using the scale relation for computing the Alexander polynomial, and this is proved using the Kaufman polynomial. You can also use here a Goritz matrix, but the proof by Kaufman polynomial is very nice. So this has a kind of nice consequence. In fact, if you fix a knot and look for the symmetric union presentation, but you say, okay, I want to use only alternating partial knot. Then you have only finitely many possibility for the alternating partial knot. And conversely, if you look to an alternating knot, then you have only finitely many possible alternating knot which have a symmetric union with a given partial knot which is fixed. So here you see already that only using that, you get some kind of finiteness theorem. And why this is true? So Tanaka was using the Q polynomial, but in fact it follows already from this old Bankwitz theorem, which says that the crossing number is bounded by the determinant. So because of the relation that the determinant of the symmetric union is the square of the determinant of the partial knot, you get the answer. So two partial knots for two symmetric union with the same knot type have the same determinant. And you have this nice question of Christopher Lamb. Are there knots with the same determinant, but which cannot be partial knot for two symmetric union with the same knot type? That seems a difficult question at the moment. That seems a difficult question. And there is no, I think, no tools to decide such a things. Okay, so my goal here would be to try to study relationship between the symmetric union and the knot type without putting any assumption on the number of twist region or on the type of the twist. And to do that, we can use the π-Orbifold group. So what is the π-Orbifold group? That's a group of the knot where you kill the square of the meridian. So it's in fact the orbifold fundamental group of a closed orbifold where the underlying space is S3 and the singular locus is K with a branching index 2. And in fact, the orbifold is a quotient of the twofold branch covering by the covering involution. So it's a good orbifold. You take the twofold branch covering, you make the quotient by the involution, and you get this orbifold. So therefore, you get this exact sequence, which will be very useful. The fundamental group of the twofold branch cover is an index 2 subgroup of the orbifold group of the knot. And the last thing is that when this twofold branch cover is aspherical, then the only torsion element in your group here comes from the meridian. It comes from the ramification. And that shows you that it's a strong group in some sense, because in this aspherical case, it tells you where are the meridian. And so you have this, all what I say works for links. Here I could have take a links, that would have the same things. But this Ferson orbifold theorem implies that sigma 2 has a tau invariant geometric decomposition along a finite, possibly empty collection of spheres and tori. From that, you can deduce that if you take a prime knot with more than 3 bridges, then this group determines the pair. And that's work for link too. So this group, for example, for link, is much more powerful than the fundamental group of the complement of a link. You have infinitely many links with the same fundamental group. It does not work with this. So why we have to avoid 2? Because when you have a 2 bridge, the fundamental group of the twofold branch cover is cyclic. The twofold branch cover is the length space. And then your orbifold group is the diedral group. And there you have many two bridge knots with the same orbifold group in some sense. But if you accept that, then you have really this group will determine the knot. And so I will take this definition. I will take that K1 pi dominates the node K2 if I have an epimorphism between these two groups. So usually the domination we like to take is from the fundamental group of the node, an epimorphism from the fundamental group of the node of K1 to the fundamental group of the node of K2 in some sense. The complement, the group of the node. That is the complement. And these are two different domination relations. But the one where you take the fundamental group of the complement does not extend to links because you have infinitely many links with the same fundamental group. This works very well for links. So I just advertise that something which is perhaps more natural to try to compare knot and links than the fundamental group of the complement. These groups, they are Hopfian by the geometrization. And so this is antisymmetric on the set of prime knots with atmos-free bridges. And so it's a partial order on this. Okay, but we will just use this domination. So here, just to say, if you have that K which pi dominate K prime, by definition, you have this epimorphism. But you look to a meridian of K, this image cannot live in this subgroup, index 2 subgroup. This is a normal subgroup, and this normally generates that. So if its image is here, all the subgroup will be here. But we take an epimorphism. So that means that this epimorphism the restriction induce an epimorphism here. If you restrict it to this subgroup, it will be surjective on this one. And so that means that this relation is strongly related to the usual relation on the set of closed orientable free manifold, which is induced by epimorphism between their fundamental group. So in some sense, if the node K pi dominate K prime, then the twofold branch cover of K will dominate in the sense of the fundamental group, the twofold branch cover of K prime. But the converse is false. So just a small application, if K pi dominate K prime and K prime is not K, is different from K, then the fundamental group of the twofold branch cover cannot be the same. Because if they are the same, they are Hopfian. And this epimorphism will be an isomorphism. And if this phi tilde is an isomorphism, it's easy to show that this is an isomorphism. And the knot will be the same. So K prime is not a mutant of K. And so a knot will not pi dominate a mutant of itself, which is in some sense natural. Okay, so why I am interested in that is because of this result of Lamb and Eiserman is that this pi domination appears naturally in the symmetric union construction. So if you have a symmetric union with partial knot KD, then the symmetric union pi dominate the partial knot. And you have something more. The image of the meridian goes to the image of the meridian, and the epimorphism kills the image of the longitude. That means, in some sense, if you usually an epimorphism between orbifold or a spherical orbifold, you can realize by a map. But this means that this map, in some sense, will be of degree 0. And so not easy to handle. But why this is true is just you look to the Wirtinger generator. So if you have a Wirtinger generator for KD, when you do the construction, you get a set of Wirtinger generator. Here too, you add for the symmetric union. And then here I have erased every orientation, and I am working in the orbifold group. So x minus 1 is x. Okay? The meridian are of order 2.
and these are the meridian. So the relation you have to read are this one. This one. This is a symmetric crossing with respect to the axis. And this one. So what you do, you take x prime, and you send to x hat. Y prime, and you send to y hat. And then here you have this S1, S2, and all generator. You send them to this unique generator. So you do that formally at the level of the group, and then you see that the map you define on the generators of your group will fulfill the relation. So it will induce some homomorphism. And it is surjective because you get all the generators. So now the idea is, okay, if I understand this relation of surjection, perhaps I can get restriction on the partial knot from the symmetric union. So just an easy example, you take two knots where K pi dominate K prime, then K is the unknot, implies that K prime is the unknot. If you read to the paper of Kinoshita Teresaka, the main result they have, one of the main results, is exactly that. If you take a non-trivial knot, you do the symmetric union, you get a non-trivial knot. That's exactly what they do. They do it combinatorially on the projection. Here you have a proof which uses the Smith conjecture, but only for the two action in some sense. And also, if K is a two-bridge knot, K prime will be either the unknot or a two-bridge knot. So if you look for symmetric union presentation of a ribbon two-bridge knot, you have only to look to two-bridge knot. And you know that if the determinant of the symmetric union is a P, it has to be P square, in fact, then the determinant of your two-bridge knot has to be P. So you have only finitely many two-bridge knots to look at. And why it's true is just because if this is a knot, this orbifold group is Z over 2Z. And if can surject only on Z over 2Z. And then that's the proof of this Z2 Smith conjecture, which goes back to Waldhausen. K prime is a knot. If this orbifold is cyclic, is finite cyclic in some sense. And if K is a two-bridge knot, then this is a finite dihedral group, but then by surjection, you get a finite dihedral group or Z over 2Z. And then here you have to use the orbifold theorem. Here you have to use not the Smith conjecture only, really the orbifold theorem. Then K prime will be a two-bridge knot or the unknot. So for this simple case, it gives you some valuable information. Now, I come back to the question of finiteness. First, does a knot K pi dominate only finitely many knots? This will mean that if it's yes, the symmetric union, if you fix the symmetric union type, you have only finitely many partial knots. I don't know the answer, but the answer is yes if the knot is small. And the knot is small if its exterior does not contain any closed, incompressible, and non-boundary parallel surface. Torus knot are small. Montesinos knot with three branches are small. Two bridge knots are small, some sense. So you have small knot. And here the result is that if K is a small knot, then the dominated knot K prime is a small knot. And in fact, K will P dominates only finitely many knots. So I want to stress that if you ask the same question using the fundamental group of the complement of the knot, what is called the group of the knot, if I have an epimorphism from the group of a small knot onto the group of a knot, it is not known that the target knot is small. It's not easy when you have boundary. Here, what makes the things work is that you can find an interpretation of an equivalence of small knots, smallness, using a closed object. And the key lemma is this one, which is kind of rather classical. A knot is small if only it's the orbifold. OK is small. And then why it allows to conclude. So we want to prove the first part is that if K is small and it bidominate K prime, then K prime is small. We will show the contraposé. We will show that if K prime is not small, K is not small. K prime not small by this lemma is the same as the orbifold associated to K prime not small. That means that it contains an orientable closed surface, orientable closed incompressible to orbifold. But when you have that, the orbifold group, as in the free manifold case, split along this group as an amalgamated free product or a national extension. And then this group act non-trivially on the Basser tree associated to this algebraic decomposition. You have an epimorphism. So this epimorphism induces an action of this orbifold group and which a non-trivial action on this Basser tree. Then in three-dimensional topology, when you have such an action, that was the Stallings and the theory of Kühler-Shannon, then you can split the manifold along the surface. But this is also true in the orbifold setting. And so you get that OK, this orbifold contains some orientable, incompressible two suborbifold, and thus it cannot be small. So in some sense, small knot, pi dominates small knot, and that will be important in some sense, interesting. But more interesting for us will be what is the p minimal knot. And here I will take an algebraic definition. K is said to be p minimal if when it's pi dominates K prime, that implies that the orbifold group of K prime is isomorphic to the diedral group or to the orbifold group of K. That seems a little bizarre. You would have expected K is p minimal when you have this relation. K is either two bridge or equivalent to K prime. But you know, the problem is that the orbifold group does not determine the knot when the knot is not prime. And so it's better to work with this kind of algebraic definition. By definition, all two bridge knots are pi minimal. And you can show that any knot with three bridges will pi dominate a p minimal knot with at most three bridges. And this knot will be either a prime knot or a connected sum of two bridge knots. So this last assertion is not difficult. It's easy from the definition to show that if a pi minimal knot is not prime, it will be a connected sum of two bridge knots in some sense. So why this is true? You look to a sequence like that of pi-ordered sequence of knots with at least three bridges. And then you show that it stabilizes, not the knot perhaps does not become the same, but the group, orbifold group, becomes the same. And so there is no assumption on primeness here. If you put an assumption of primeness, you could have said, okay, it stabilizes for the knot type. And this is just because you get this sequence of epimorphism, and it induces this sequence here of epimorphism between free manifold group. And then this sequence will stabilize by a deep result of Grove, Yule, and Liang in 2021, where they prove this result It's a consequence of some Noetherian result in geometry group theory in some sense. So, and so using that, you can show that you have a minimal knot. So you may say, why minimal knots are interesting? Here, you have a kind, it's an easy P minimal, you can an obstruction for a P minimal knot to be a symmetric union. So you take a P minimal knot with at least 3 bridges, and you assume that you have a condition on the torsion number of the twofold branch cover. You want that this torsion number, so I remember that the decomposition in a product of cyclic group where D1 divide D2 and D2 divide Dn in some sense. And you want that this decomposition verifies that the product of the n-1 first di does not divide Dn. Typically, if you take Zp cross Zp cross Zp, P square does not divide P. Typically, this is the condition in some sense. Then, if you have this condition, K cannot be a symmetric union. Why? To prove that, the following lemma is needed. You have a symmetric union with partial knot KD. If K is knotted, then KD cannot be equivalent to K. So you cannot, if you take a knotted knot with, you cannot recover the same knot by doing the symmetric union construction. But in fact, you have more. You have that their orbifold group cannot be isomorphic. So what it means that if you have a symmetric union with partial knot KD, if it's pi minimal, then KD has at most 2 bridges. And so you have only to rule out the case of 2-bridge knot. And okay, perhaps the time is running. I will not do it. The lemma is not difficult. I will just go around. Then, okay, I will just go around. Then I want to speak about Montesinus knot, and I recover what is it. It's a cycle of rational tangle, and that's a picture of a rational tangle. And I take the notation like in not info, the tabulation, and that's a number of this rational number which describes a rational tangle. And the twofold branch cover will be a closed orientable ciphered fibrane manifold with R exceptional fibers. This is the type of the exceptional fibers, and with base S2. So you have this proposition. If the knot K pi dominate K prime, if K is a torus knot, K prime must be a torus knot. If K is a Montesinus knot, K prime will be a Montesinus knot with less number of rational tangle. So in some sense, simpler. Or, because K prime may not be prime, if K prime is not prime, you can get a connected sum of N1 2-bridge knot and N2 elliptic Montesinus knot. Elliptic means that the orbifold group of this is finite. And that means the Montesinus knot is elliptic, is this triple is platonic. It's 2-3-3 or 2-3-5. So here you get a strong restriction on the possible knot when you have a connected sum. Here you get just a simpler Montesinus knot. And the last is, in some sense, the generalization of Montesinus knot or 2-bridge knot was this arborescent knot of Bonaon-Zibedman. I take as a definition that a knot is arborescent, is this twofold branch cover, is a graph manifold. We cannot show that K prime is arborescent, but we can show that at least the geometric decomposition of the orbifold contains a ciphered piece. So, for example, the twofold branch cover of K prime cannot be hyperbolic. So there is some of the arborescence which appear here. My guess is that perhaps this has to be arborescent, but we don't have the proof at the moment. So when the orbifold group is infinite, torus knots and Montesinos knot cases follow from the characterization of a closed aspherical orientable Seifert manifold. As you know, this is a manifold such that the fundamental group has an infinite cyclic normal subgroup. That's what you use in some sense to handle this case. The arborescent knot case follows from something which is more, in some sense, interesting. If you take a rational homology sphere, which is a graph manifold, and you take N, a closed orientable irreducible manifold, where there is no Seifert piece in the GSG piece, then if you take any homomorphism of the fundamental group, it must be trivial. And so then, in some sense, then it could not be surjective if it's trivial. And you prove this by proving it for Seifert manifold and making an induction on the number of Seifert pieces for the graph manifold. So this we don't know. If K is arborescent, is K prime arborescent? In some sense, you ask, if I have an epimorphism from the fundamental group of an arborescent manifold to a free manifold, is it arborescent? So I will finish. If you look, the Montesinos knots here, 11A 103, 11A 165, Illinois on way 201, they are the only alternating Riemann knot with 11 crossing for which a symmetric union presentation is not known. These two knots are P minimal, and hence the only possible partial knot are the torus knot 29, that's the knot 911 in the tabulation, or the two branch knot 61. If you look this one, there is one more possibility, which is the Montesinos knot 820. And you know, the real difficulty is how to rule out these possibilities, how to rule out this two bridge knot. And the proof is just a case by case analysis to rule out all possible cases, and it uses some geometry of triangle groups. But really the difficult problem is that how to rule out the two bridge knot, the case that the two bridge knot can be partial, that the partial knot can be two bridge, because in this case, they all have the same, it is incredible, they all have the same homology. And in fact, this one and this one, they have the same Alexander polynomial. So at least if we restrict to the even symmetric union presentation, where the twist numbers are even, then we can do it for this knot by using twisted Alexander polynomial. This knot cannot admit an even symmetric union presentation because the degree of its Alexander polynomial is 6. And if it's an even symmetric union presentation, it's Alexander polynomial has to be the square of an Alexander polynomial of the partial knot. So the degree has to be divided by 4. So here you know that it cannot be. But we don't know what happened. I finish by this question. If I have a knot, if the determinant is 1, does it admit a symmetric? It is a symmetric union, okay. The determinant is 1. Does it admit a symmetric union presentation with an unnoted partial knot? You know, this seems very, very hard. Ruling out two bridge knot if you have sufficiently, if this is sufficiently complicated, this homology, perhaps you cannot do. But when the partial knot, when the discriminant in one, how to rule out the trivial knot? This seems to me a very difficult question. Thank you. I will finish on that. Thank you very much.
Oh, thank you, Michel. What an amazing talk. Thank you so much. So I will stop recording.